Thank you very much. I was planning to talk about Pointwise convergence problems in ergodic theorem. Notice that I recently realized that Tomac Sharek covered essentially everything what I wanted to say. So I changed the topic a little bit, and we will mainly talk about Poirot theorem from the ergodic point of view perspective, using ergodic theory, and the main tool will be norm convergence and norm convergence methods in ergodic theory. So two or 3 weeks ago, we had a nice meeting in Van Level where I started this story about Roth and Semeredi, and I give a proof of Roth theorem by using classical Fourier methods and higher order Fourier analysis. And so there's alternative proof by Furstenberg, which uses ergodic perspective, and this is what I plan to present during this week. So we will have some mini course in ergodic theory to review basic methods from ergodic theory, which will be necessary to understand this problem. But let me start from some historical background. Essentially, the first few slides will be exactly the same as in Van Level. The story starts in 1936 when Erdős and Turan formulated this conjecture that suppose that we have a subset of integers with positive upper density, which means that this quantity here, the soup of this quantity is positive. And then the conjecture states that for every integer, there exist infinitely many arithmetic progressions inside set in question E. So which means that we can find in this set configurations of this form. And in fact, in other words, we can state that, for every, so there are arbitrarily long, there are infinitely many arbitrarily long arithmetic progressions inside this set. So this is where this audacious conjecture of Erdős and Turan states. And so here we have some examples. So let's first examine these examples, and then I would like to put some comment personal comment. So if we consider, for instance, arithmetic progressions with spacing Q, then we can easily see that this quantity is 1/Q. So on the other hand, on the other extreme, we have the set of prime numbers, and we can observe that this density is 0 because of the prime number theorem, where we have this asymptotic formula. And a beautiful example is the set of square-free integers. So we take all integers and we remove all squares and multiple squares. This is how we get square-free integers. And it turns out that if we use a little bit of counting or Fourier analysis, basic Fourier analysis, then we can show that this density of the square-free integers is 6/π². So therefore, this is non-zero, and this density is non-zero. And so I have to say that when first I learned about this, now this is a theorem, famous theorem of Semeredi. It was put in 1974. But when I learned about this, I couldn't believe that something like this can be true, and especially in the context of this square-free integers. So this is the set of the positive integers with positive density, and in this set can we find infinitely many arbitrarily long arithmetic progressions. So on the other hand, so this is a very remarkable statement because here the assumption says nothing about the structure, but the conclusion is very structured in the sense that, so it says that inside E, the set of integers satisfying this property, this metric or statistical property, it inherits additive structure from the set of integers. Additive structure in the sense of the existence of this patterns that constitute consecutive elements here, then the difference is constant. So that's the conjecture. And so here, this is the current state of knowledge about this conjecture. So now this is the theorem, famous theorem of Semerelli. But before Semerelli proved this, there was Klaus Roth in 1953 who verified Herder-Sturm conjecture for arithmetic progressions of length theory. And he used Fourier methods, in particular circle method, to prove this theorem. And he also, in some interesting sense, quantified this. So his method, this was not only by showing that he proved this for k equal 3, but he also quantified this. In a moment, I will tell you in what sense this can be quantified. But 20 years later, Semerelli proved this Herder-Sturm conjecture for arbitrarily long arithmetic progressions by using some tools from combinatorics and graph theory. So this was it's a very big paper with still very, very difficult and so this is what we owe to Semerelli. This is something. The key tool was the regularity lemma, which is an important tool these days in additive combinatorics and small graph theory, and this was invented in this paper. So this paper uses elementary methods, but it's still very, very intricate. And 3 or 4 years, 2 years, in fact, 2 years, it was 2 years later when Furstenberg started to think about this and about Semerelli theorem, and he gave a conceptual new proof of Semerelli by employing ergodic methods. And so he was able to interpret Semerelli theorem in terms of ergodic language, which now, thanks to Furstenberg, Semerelli theorem is a certain kind of multiple recurrence theorem in ergodic theory. So in a moment, I will formulate what the multiple recurrence theorem is. And so finally, Gowers in 2001, he quantified Semerelli theorem by developing something which these days is called higher order Fourier analysis. Very powerful set of tools to understand this kind of problems. Okay, so let me now tell you what is the quantified version of Semerelli. So here, in order to formulate this quantified version, so we have to introduce the following quantity, the following function Rkn, which denotes the size of the largest subset of the first n integers that contain no arithmetic progressions of length k. So in other words, in this set we have. So this is the largest subset which does not have this configuration. And so Rolf originally proved is so this is what follows from Rolf methods from classical Fourier analysis, that this function is controlled by this one and over log n, and that's the bound. This is what we understand by quantifying version of Semerelli theorem, and for Roth, it's possible to derive this. Now, this was, this paper in fact was a trigger to understand, this function, and now we have a much better bounds. But I'm not going to talk about this. But these days we have fairly satisfactory answer, how this function behaves. But okay, but so let me emphasize that these classical Fourier methods are limited to the configurations, to arithmetic progressions of length 3. And so I hope that I explained this in one level, because we discussed this proof in details. So I hope that I conveyed some ideas, and now you have those who attended have some sense of why you have this and what's going on here, and why in this context classical Fourier methods are important and efficient. But so, and Samarelli and Furstenberg, so this is what follows from Furstenberg. We only think that this function Rk of n behaves like little O of n. So this is because both Samarelli and Furstenberg, they use axiom of choice. So that's the simplest explanation in the proof, and this is why they have this. But and then I think that was the reason why Gowers started to think about this again and try to quantify Samarelli theorem he wanted to understand the behavior of Rkn or arbitrary k in the context of Samarelli arbitrary long arithmetic progressions. And thanks to Gowers, by using this higher order Fourier analysis, which is some set of tools, including Gowers uniformity norms, Gowers inverse theorem, and things like this. We also discuss this in one level in the context of Roth. So we are able, in general situation, to derive this bound and over log n to gamma k. Gamma k here is a very small number. Usually, originally this is 1 over 2 to some large power, and this 1 over 2. This reflects, how many times Cauchy-Schwarz inequality is used in this proof. So this is why we get this. So this can be, so originally this is a very small number. Now we have tremendous improvement, which was recently done by Length and Saf and Sauni, and this is now we have much better bound in this general setting. But I'm not gonna to touch this. But let's
Mariusz,
yes.
In the last line, the constant, because there is inequality with the constant, yes? Does the constant depend on k?
Yes, it does, yes. So yes. Okay, so now, but now I would like to talk about this ergodic. So here we will talk about the ergodic context, and this is very elegant and very beautiful, and it's very powerful in many contexts. So and the nice thing about this is that we will use some soft methods from classical functional analysis, which are nicely accommodated to this ergodic situation. So let's start with basic setting of measure preserving transformation. So what we'll consider, so if we have two measure spaces, so the measurable transformation between measure transformation, which is defined on x1 and taking values in x2, this is a transformation that satisfies this condition. For every measurable set in this codomain, the preimage of E is also measurable in the sense of this sigma algebra. And so a transformation.
Sorry, what is the meaning of the square bracket here? Around E?
This is preimage of E. This is just, okay, so this is This is just pre-image, yeah.
Just, I mean, I understand that T minus one, but I just didn't, I never seen the square bracket before.
You just
Yeah.
put the argument into the.
Or it's just,
That's bracket.
okay, all right, fine,
Okay, yeah, this is just pre-image.
okay.
So,
I thought that that's some kind of special thing.
uh, so. Okay, so, and measure preserving transformation is measurable transformation which satisfies this identity. So if for every set E, measurable set E in M2, we require to have this identity. So this means that T is measured preserved. In a moment, we will see some measure preserving examples of measure preserving transformations. And so we will say that invertible measure preserving, so T is invertible and measure preserving if T is measure preserving is bijective and T inverse is also measure preserving. And so a measure space, we will think that usually, for this a context of ergodic Ramsey theory, we can see that we work with finite measure preserving systems, and measure preserving system. On the other hand, this is measure space which is equipped with measure preserving transformations, and will be denoted by this. Okay, so that are basic definitions, but in order to get some ideas about this definition, so here we have some bunch of examples. Presumably the simplest one, and this example is important from the point of view of pointwise convergence problems in ergodic theory. This is the shift integer system. So this is the set of integers with sigma algebra of all subsets of Z and counting measure and shift operator, which takes an integer x and transform it to x plus 1 or x minus 1, depending on the context, if you want to consider the right shift or left shift. And this is obviously measure preserving system because counting measure is translation invariant. So that can be easily checked in this context. The other important example from the point of view of problems in equidistribution, this is the circle rotation system. So this is the torus with the sigma algebra, Lebesgue sigma algebra, and the Lebesgue measure induced on the torus, and rotation map by irrational angle, so which is this transformation. This is the x plus alpha mod 1. So this is the rotation by irrational angle. And then here we can check that this is also measure preserving transformation, because of the fact that Lebesgue measure is translation invariant. Another important system from the also from number theoretic and some statistical application. This is the circle doubling system. So this is also torus with Lebesgue measure and Lebesgue sigma algebra, and the doubling map is defined this way. So we multiply by 2 modulo 1 on the torus, and this also can be checked. This is measure preserving system. And finally, what is in many situations very interesting and convenient is to consider is to see continued fractions as a dynamical system. And so the corresponding dynamical system for the continued fractions is interval 0, 1 with the Lebesgue measure, and the Gauss measure, which is the Lebesgue measure with this density. Everything is normalized to half mass 1. And the continued fraction expansion, continued fraction map, this is Px equal 1 over x modulo 1 whenever x is equal 0, and 0 whenever x is 0. And the nice feature of this is that, if we take a number in the unit interval and we consider its continuous fraction expansion, then the nth digit, this is t, can be seen as a tn minus 1 iteration of x, for the number in question. So that's a nice thing that, the corresponding digits in the continuous fraction expansion can be seen in the direction of the number from the unit interval. So, and from here, so having this interpretation, we can derive many nice statistical properties of continuous fractions, but which can be deduced, for instance, by appealing to the ergodic theorem. So, but we want to talk about. So our aim will be to talk about this combinatorial applications. So we'll go more into ergodic Ramsey theory, where which is the part of ergodic theory where this combinatorial applications can be made. But finally, let me also mention that here we have an interesting example of Bernoulli shift. So this is the model of the set of possible outcomes of an infinitely repeated toss of a third point. So we consider Cantor set. This is the sequence. This is the set of infinite binary sequences. This set is a compact space. This is equipped with this nice product measure. Each mu. This is a measure of this form, which is 1/2 or 0 or 1. And so the shift operator, which is given by this formula, it preserves this measure here. So this can be verified by. It's a simple exercise for measure theory. But what's important, so which at the first glance it's not obvious, but if we start to think a little bit, then we can see that if we consider this Cantor function, which maps the Cantor set to the unit interval, if we identify the totals for the unit interval, then we can see that it has this nice property that phi of sigma, this is the shift. This is like application of doubling circle mapping to phi, and we obtain this. So therefore, we see that these two systems are isomorphic. They can be identical. They are isomorphic up to countable sets. So if they are isomorphic from here, we remove all infinite all elements which have which depends only on infinitely many entries. So these are identified with the set of rational numbers on the unit interval. So from this point of view, these two systems, the doubling circle system here and this Bernoulli shift are measurably isomorphic. Okay, and now we have some idea about the measured periodic systems, and let me tell you a few words about the Furstenberg ideas, how he figured out that this Semereti theorem can be interpreted in terms of this ergodic language. So an important theorem in ergodic theory, which we try to prove today, I will try to give you two proofs of this result. This is the Poincaré. So this was the starting point of ergodic theory, and it asserts that if we have a finite measure preserving system, and if we consider a measurable set of positive measure, then the measure of this event is positive. So which means that the orbits, if we start from E, it returns to E. Orbits of T, it returns to E infinity of. So this is what this inequality says. And so the motivation comes from statistical or classical mechanics. So if we consider So here is what was the motivation for Poincaré. If a cloud of gas, which is initially confined in the left compartment of the vessel, is released into the right empty compartment, then after sufficiently long time, the gas particles will return to the left compartment. So not necessarily to their original configuration, but they will go back to the left compartment, leaving the right compartment empty. So that's what Poincaré reference theorem says. And so what's important that this will happen infinitely. We don't know, what is the first time, when this happened, but we know that this will happen. And this is how Furstenberg started to think about arithmetic progression, because we can see that, if we consider a subset of integers, then arithmetic progressions, they have this nice dynamical interpretation. If we want to find, these configurations here, then if we use shift operator, then we see that this set can be written as a set of this form. So therefore, we see we want to understand, the nth iteration of x under the shift operator. And it turns out that if you want to show that this set contains arithmetic progressions of length k, or in this case, of length k plus 1, then we have to show that this set is non-empty. So, and this can be thought as a result about recurrence in the code. In fact, Furstenberg multiple recurrence theorem asserts that for every integer, the measure of this event is positive for some n, and in fact for infinity n, as we will see. So, and this is what is called in the literature multiple recurrence theorem, and I will try to convince you that this is ergodic. So here we have some first attempt to convince you that these days, these kinds of results in ergodic theory are, in fact, ergodic interpretations of some array or ergodic counterparts of some array. But here, let me emphasize that there is one problem, because here you can see that we interpret everything, in terms of integer shift system, and everything would be fine, but there is a little issue that Poincaré recurrence theorem is only true when we consider finite dynamical systems. So if we draw this assumption, if we, for instance, want to see what happened in the integer shift system, then this is not true. The conclusion doesn't hold. This is only true in a finite mechanical system. So therefore, here, even though we have this nice interpretation in terms of shift operator, then we cannot expect results like this whenever t is a shift operator. But this can be so we will see how to overcome this, and this was the a beautiful idea of Furstenberg, who proved something which these days is called the Furstenberg correspondence principle, which is a second bridge between the ergodic world and this additive combinatorial world. So in a moment I'll tell you. So here is the Furstenberg correspondence, but let me tell you what Furstenberg proved and how his theorem was formulated. So this is his theorem. So take a look, so we have a probability measure preserving system. This is our assumption. We take a measurable set of positive measure. And Furstenberg showed that linking of this average is possible. In fact, so he proved a stronger statement. So, and now we see that if linking of this average is positive, then it means that for every k, there exists in particular an integer, and in fact, infinitely many integers for which we have this. So therefore we have this multiple recurrence theorem. And now there's a question, how this can be used to deduce the result on the set of integers, because this is what we want here. So there is another important tool, which is called the Furstenberg correspondence principle. Very beautiful result. So if we consider subset of integers with positive density, upper density, then this implies that there exists a probability measure preserving system and a measurable set with this property that the measure of this set in this new probabilistic measure preserving system is equal to the upper density of A. So which means that this is positive. So therefore we see that here we were in the assumptions of the previous theorem, the Furstenberg theorem. And moreover, the second part of this statement says that this quantity from above is dominated by the density of this set, where S here is a usual shift operator on the set of integers. So therefore, you see that this, the assumption on this, and this equality implies that we have this. So therefore, this here now implies that we have this, and if we apply, this is non-zero, and if we apply the second part of Furstenberg correspondence principle, it says that this is non-zero. But if density of this set is non-zero, then this means that this is non-empty. So therefore, if this is non-empty, then this means that we can find arithmetic progressions of length here k plus 1 in A, and this is what we were looking for. So that's how we get this correspondence principle. And this correspondence principle, so at the first glance, this statement it looks very mysterious, but in fact, the idea to construct this measure preserving system is very simple, and it comes from basic results from set theory. So when we want to show that the subset of integers have a cardinality continuum, so this is what we do. We construct a bijection between all subsets of integers and the counterset. And this bijection is given by this formula. So let me put this. So here let's consider the power set of the set of integers, and we know that this set has the same cardinality as the counter set. And this bijection can be given by this. So for every A element from here, which is a subset of integers, we just associate the characteristic function of A. And this is element of, so here A is a subset of N, and this is of course this is characteristic function, so it takes value 0 and 1. So this is the element of the counters. And now we see that, and this is in fact, what makes this construction possible. So instead of thinking about the set of integers itself and shift operator, we start to think about the subset of integers and transfer everything, to the counter set, where we have nice compact structure and moreover shift operator acting here, and this is essentially the model for the Furstenberg correspondence principle, which allows us to interpret this kind of inequalities here in this system, and by the correspondence principle transfer everything to the set of integers. So we will talk in details about the Furstenberg correspondence principle, hopefully. So I try to show you how the proof works, but this is essentially the idea, that comes from this basic observation, which allows us to show that these two sets have the same cardinality. Okay, so that's and our aim, will be to prove. My aim will be to prove this theorem, this result, for k equal 2 here. In other words, we want to show the Roth theorem for arithmetic progressions of length 3, and by using this ergodic methods. And so I have to tell you that this ideas of Furstenberg were very influential, and now we have very too far-reaching generalizations of Furstenberg theorem, Samarelli Furstenberg theorem 1. This is beautiful results from 1996 of Bergelson and Liebman, to prove that if we consider that, in other words, instead of linear configurations, we can consider polynomial configurations, and they also exist in sets with non-vanishing upper density. So in other words, it says that if we have a probabilistic measure preserving system and we consider polynomials, arbitrary polynomials, each having 0 constant term, and we consider set with positive measurable set with positive measure, then lead-in of this is positive, which in other words implies that here the measure of this event is positive infinitely often, and in particular implies that every subset of integers with non-vanishing upper density contain polynomial patterns of this form. So that's what Mariusz and Liebman. In fact, they proved this in a much more general setting in a multi-dimensional situation when one can consider not only the configurations on Z, but also on ZD with more sophisticated multi-variable polynomials. But this is so for our purposes to get some sense, how important ergodic methods were. So this is sufficient. On the other hand, these ergodic methods were combined with some higher order Fourier analysis, were important also in the proof of Green and Tau from 2004, which is an analog of Samarelli theorem in the set of prime numbers. So we remember that Samarelli theorem cannot be applied to the set of prime numbers because it has 0 density. But if we consider subsets of primes which have relative positive upper density inside primes, or we can say that this is positive upper relative density, which means that this quantity is positive, then there are infinitely many arithmetic progressions for any k inside E. Right. So this is the famous result of Green and Tau. And so that's what can be okay, so these two results were significantly influenced by this ergodic methods and the progress in this ergodic transitive. And now let me our aim will be to start from the proof of Poincaré recurrence theorem. I would like to show you that in fact, the simplest proof of Poincaré, this is just pigeonhole principle. So in a moment I'll try to convince you. And the other proof, which is more quantified, falls from the von Neumann ergodic theorem, which we also prove. And all these are will be important ingredients, in developing our discussion. And so I want to go through the details to make sure that we can follow everything. And so if we have a measure preserving system, so it's good to consider associated unitary operator, which can be defined in this way. So for every square integrable function, we can introduce ut of f, which is f composed with t. And then we immediately see that this is a unitary operator because of this identity, because t is measure preserving, because mu is measure preserving, sorry, mu is t invariant. And so therefore we see that this is isometry between these two alpha spaces whenever this space is measure preserving. And moreover, we can observe that this is even unitary operator if T is a bijection. But in this generator, this is only isometry. So we might only have isometry in the sense that the length of the vector H is preserved. So we have this identity. And so this operator here in the literature is called the Kaplan operator of T. And it will be, so I will, usually when I refer to this name, the Kaplan operator, I will have in mind this operator, but this is composition of F with T. Okay, and now let me present the proof of Poincaré recurrence theorem. So in Poincaré recurrence, in its simplest form, it says that in every finite measure preserving system, if we have a measure of this set with positive measure, then there exists X and an integer such that T and X returns to E. And so in order to see how this works, so let's consider, so we can observe that we have an infinite sequence of sets and all have positive measure, and in fact, measure of each member of this, of each element of this sequence is measure of E, because T is a measure of preserving transformation. And so if we assume that all these elements here are pairwise disjoint, then on the one hand, we have this, that the left-hand side is infinite, because we sum infinitely many numbers, positive numbers. By countable additivity, we have this, and then this is a subset of X, so therefore it's dominated by the measure of X, the entire space, which is finite, so therefore we get a contradiction. So therefore, we must have at least two indices by the pigeonholing that they are non-empty. And therefore, if there are two integers K and M which are non-empty, so there exists Y in this set with this property. And now we see that if we apply, then this is the element that we're looking for. This has this one. If we take n equal n minus k, then this is one. So that's the simplest form of Poincaré recurrence. But it can be quantified in a very nice way, and you will see that this quantified version will play a role in many contexts. So I would like to build this theory to show you that how important it is. And also, before I prove, let me also comment that before I prove Roth, we would like to prove. I will show you, which is much simpler proof of Sarkozy theorem. The Sarkozy theorem is also some results from additive combinatorics. It says that if we consider any set of which has any subset of integers which has positive density, then we can find two elements whose difference is a perfect square. So that's a Sarkozy result. And I would like to present the Sarkozy by using ergodic methods to get some feeling how these methods can be used, and then we will talk about Roth theorem by using the machinery graph. So here we have mean ergodic theorem, which is also called the normal ergodic theorem. It's a result about some kind of statistical result, or you can think that this is some result about predicting the future. And so it says that if we have a Hilbert space with normal operator, so it works also for some contractions, but for our purposes, normal operator is fine. If we normal means that U commutes with its adjoint, and if we consider this, if we add this assumption that they are uniformly bounded in the sense that the sup of the norm is a finite number, then for every vector, for every function from this Hilbert space, this kind of averages, they converge to the projection onto one-dimensional space of U invariant vectors. So in other words, to this space. And so that's so in a moment we'll see that this is a very important result. And let me give you a proof, which is based on the Riesz decomposition. Sometimes people say that this is von Neumann trick, but I think that this should be attributed to Riesz too. So we can see that because this is one-dimensional closed subset of closed subspace of H, then we can decompose our Hilbert space into I and orthogonal complement. But now we can observe that this orthogonal complement is given by this explicit formula. This is the closure of the image of U minus identity. The closure, of course, in the Hilbert space. And so it suffices to show that I is equal to the orthogonal complement to this space. And because U is normal, then we can see that so I, this is the kernel of this operator. By normality, this is the kernel of this. So here the normality is 0. But now we know that this is the orthogonal complement of this. So that's how we get this identity. And so once we have this identity, then the proof of this convergence is fairly trivial, because this is what we do. We use Riesz decomposition, and it suffices to verify this convergence on function that lives here and function that lives here, or in fact in this not but then by density it can be deduced for all H here in the closure of R Q minus 1. So using Riesz decomposition, if we apply our vector, if F is from I, and we apply our averaging operator, then we see that this immediately converges to F, because this is identity. Then U on F from this space is identity operator. So therefore, there is nothing to prove. And now on the orthogonal complement, we have to prove that this converges on this vector H from here. This converges to 0. But first, by simple density argument, we can assume that H is from this space, and so therefore H has this form. And now we can observe that if we apply our averaging operator to H, and we use the telescopic nature of this expression, then only the first and the last term may survive. So therefore we have this. And here we use triangle inequality and the fact that our operator is normal. It was an operator which has uniformly bounded norms. So therefore, this can be dominated by 2 times C. C, this is this quantity here. And now we can put 2 times C divided by this, and this converges to infinity. So therefore, everything converges to 0. So and that's how we get the second part. And then, as I said, we use the density. So every element from here can be approximated by a sequence that lives here, has this property. So therefore, we can deduce what we want for arbitrary H from this space, from the closure of the image of U minus. So that's how we get von Neumann's ergodic theorem. And so I intentionally formulated this in this form that we start summation. Originally, it's formulated that with summation is taken from n equal 1 to n, and we divide by n. But here, I want to have this more general form, this kind of uniformity, which allows us to deduce some nice things about later on when we will talk about some applications. And immediately when we apply this to Kopman operator, then presumably this is the so we can reformulate, rephrase the von Neumann ergodic theorem in this part that this converges here, in particular Kopman operator, which is unitary, which is in particular normal, converges to the projection to this onto this one-dimensional closed subspace of OP. And so now we can observe that ergodic averages are useful to detect recurrent points if we apply this result here to if we apply this average here to the characteristic function of the set E, then we see that this is the normalized counting function of how many times this orbit returns to E. So this is the counting function that counts the number of visits of Tn in E, Tn of x in E. And so therefore if we establish that this has a limit, then this converges, then as we know from this, then we can say something about the recurrence. And in fact, here we have this proof, which is it's a pinch recurrence theorem, but this is in fact a quantified version of Poincaré, and von Neumann's ergodic theorem can be used to deduce this result. And so this is a fairly strong statement, which, as you remember, Poincaré originally was formulated that that this is non-zero for infinite many integers, but now we can show that this holds in fact, and the lower bound can be so this form. And moreover, here this is what's important, that also we can deduce that this set is synthetic. So which means that there exists an integer depending on the epsilon with the property that this set has this property that has a non-empty intersection with any interval of this form for any integer, positive integer. So this means in ergodic Ramsey theory, this means that these sets are the set with this property are called synthetically, play an important role in Ramsey. But now let me show you how to deduce this. So by von Neumann ergodic theorem, which is applied to this characteristic function of E, which has positive measure, so we obtain. So in fact, here we take the scalar product of ergodic average with this characteristic function. So therefore, we obtain this, and from by Cauchy-Schwarz, this converges to this. And now, because this is projection, so then this is equal to the L2 norm of PT acting on the characteristic function of E. And now we can observe that this is equal to this. Here we have some sequence of equalities. And this from the fact that so what do we okay, so we split this okay, because one is orthogonal to the so one is an this is in the space of T invariant functions, so this is orthogonal to the orthogonal complement of this, which is so here, okay, so here we split this, express this as this plus the orthogonal complement, which is this minus this, and one is orthogonal to the orthogonal complement of this. Then therefore we have this identity here, and now we use Cauchy-Schwarz and use the fact that this is a probability measure space, and we obtain this, and because PT and sorry, and now what?
Wait, well, something right.
What was your question?
No. the first,
This one,
this, no, that's is correct.
this one?
No, yes, this one.
Yeah, okay, so here we split this into.
Could you flash the light?
So we have this decomposition,
Mhm.
okay? And now one, this is orthogonal to this, because this is eigenvector of Kopman operator, okay? So,
So it's invariant.
yes. Yeah. So therefore we have this, and now we use Cauchy-Schwarz, and once we have, we see that this converges here to this, and we have lower bound for this, and this has positive measures, so therefore everything here. Yeah, so this converges to essentially this, and for infinity many, and we have this this inequality. So that's how we get this Keynesian recurrence here, and yeah, and we'll see that this is, especially this syntheticity will be important. I didn't want to introduce this name, but you know, in the literature it's called this it's synthetic will be important for our applications. Okay, so I think that it's a good time to stop here, and tomorrow we will start from the concept of ergodicity and try to go further to prove some interesting to derive some interesting consequences by using this algorithm. Okay, thank you very much.
Yeah, there is no, there is no clapping, sorry.
We thank the lecturers that at the end of the course. And it's practice. So, yeah, any question for Mariusz?
Yeah, could you go back to Becker's on Newton theorem? So does this last part, does it have a combinatorial proof?
Yes.
Yes, but for certain polynomials, I think this is Paulus Prendivial.
You mean the green column? That was the
Do you mean Greenthal or Bergasolini?
Becker's
well,
Yeah, so I think that for
Yeah,
polynomials
yeah.
with distinct degrees, this is
Yeah.
Paulus and Prendivial. Yes, and Paulus Prendivial for x plus n square, and Paulus for arbitrary long configurations whenever P are polynomials of distinct degrees. So that's the current state on the knowledge.
and there is another case like x plus n square, x plus 2n square, x plus kn square. So if the common differences are power, that's plenty.
Right,
Right in the region.
This is homogeneous kind
Yeah,
of.
the homogeneous.
A question for the Keynesian theorem. Just a question, historical question. This is original proof, or is rather a new proof of this theorem?
No, I think that, okay, so I learned about this from Bergelson's notes, so I don't know if this is original. I can tell, I don't know, I haven't checked in the literature, so.
No. Yes, so it's, yeah, then, thank you. And we have a great deal further to.
We have one more lecture.
Yes.